Greetings! We've been learning propositional logic and boolean algebra in chapter 2, and some of you might be wondering, what good is this? Why are we learning about this? When could this ever be used? I want to mention a real-world application. Some of this material is related to those presented in chapter 12, section 4 and 5. We will not have time to cover that, so I'm here giving you a glimpse of it. Before we begin, I have to remind you what a function is. And you know this, a function maybe of several variables, maybe it looks like this, sine of x times y times the square root of z. These are the kind of functions that you're used to, maybe not so many variables, but you're given some real numbers and then you evaluate them and then you get some real number back. This is actually not a function. This is how we often record functions. This is simply an equation or definition for a function. The function really is something that takes in numbers and then output numbers. But more abstractly, a function is something that takes in stuff and outputs stuff. So here, let's consider a Boolean function. This function will take in Boolean values and then output Boolean values. One way to, instead of writing a formula, we know that to describe behavior of Boolean things, we can make a truth table. So here, let me make one. We have 3 variables, and by now you're very familiar with how to make truth tables. Alternate true falses here, all trues, all false, and then alternate true, true, false, false, true, true, false, false. Now there are this many, 8 different ways I could enter true or falses into the function f, and then the output is something. And usually what you've done is you have an equation here and then you calculate the truth value. Let's go backwards. Suppose you have some behavior you're thinking about, and this could be any behavior. Let's do something arbitrary, like maybe true, true, false, true, true, false, true, false. Just any sequence of trues and falses. So this is the kind of behavior you want your function to have. So how do we write out a formula? There's a lot of ways, but one of the most methodical way is if we just simply mention the true cases and then OR them together. So here there are 5 true cases. How about let's say the first true case. That says that x and y and z are all true. The second case, so let's OR that, or perhaps x and y are true, and we insist that z is false. Right? So one way to insist that is to insist that we have the negation of z. Or you can list the third one. Now this is where x is true and y and z are false. So list that x and not y and not z. By now, I hope you get the gist and you're bored and you don't want me to actually write out the next 2. So I'll write ... there. There's 2 more clauses. So with these 5, the only way to make this equation true, not equation, this expression true, is if you put in x, y, and z with truth values of one of the 5 choices, and then that will make this true. And then if you use any of the 3 other combinations for x, y, z being true and false, it will not make this true. So in this way, we have translated a truth table backwards into an expression. By the way, this is called disjunctive normal form because it has a bunch of disjunction. Disjunction is OR, so a bunch of clauses ORed together. So what I want to say is that think about how computers work. You're inputting things. You might know that computers in the internal processing are just a bunch of zeros and ones, or perhaps true and falses. You can think of that. It's really high and low voltages. And then there's some kind of combinations of these true and falses. And then at the end, it outputs some kind of true and false. So everything on the computer can be modeled as a Boolean function. And what we've shown here, this is a very simple case with 3 input variables and 1 output variable. But you can think of it as even more a longer truth table. You can always write down the expression. So a conclusion we have, which I'll label as a corollary, we'll learn what corollary means later. So a conclusion is that all Boolean functions, or you can think of all Boolean behaviors, like if you want your computer to do something, can be encoded with the operators and, or, and not. Using these 3 binary operators, you can form things like this and then encode any truth table you want, no matter what. I didn't have to do true, true, false, true, true, false, true, false. I could have given you any sequence of truths and false, and you could have written this expression out. So anything can be written with just these things. And what that means is anything we can compute using a computer can be encoded just using these 3 operators: true, and, or, and not. And some of you studied physics might have seen these diagrams before. This is an AND gate, this is an OR gate, this is a NOT gate, where you have 2 inputs and then and the output is a signal that's the AND of the 2 input, and here's the OR, and here it inverts the output. And so what this means is that any behavior you want to check, for example, perhaps you have a user typing in a credit card number. It's a 16-digit number. You can encode that using binary numbers, and then so it's a bunch of truths and falses to encode that 16 digits. And then you can have a Boolean expression like this that check whether that's a valid credit card number, because not all 16-digit numbers are valid credit card numbers. There are some rules about what numbers, and you can add them together, do some calculation to make sure that it's actually a valid credit card number. And that's something you can do as a Boolean function, and therefore can be modeled using AND, or, not, and therefore can be made physically using these gates that you learn in digital electronics. And what I want to say is that so we haven't really used the power of Boolean algebra yet, but notice here this expression could get really, really long. I could perhaps attempt to write a shorter expression using other symbols. Let's see. So if I look at these 5 truths, it looks like I don't know. I should have prepared this. So let's not do this. But I could, maybe there's a shorter expression that this function could be written as not this long. And Boolean algebra theory gives us techniques for minimizing the length of this expression by writing it shorter. Again, using AND, or, and, not, maybe we don't have to write it all this long. For instance, I can see here, instead of saying x and y and z, or x and y and not z, I could rewrite this part as x and y and be done with it. Right? The and z and not z, we can use distributivity to factor out, pull out the x and y, and then z or not z will turn into true, and then you can use, and then by the identity you can get simplified to this. So by now I think you know how to do this. So using those techniques you can simplify these expressions, and maybe you can simplify it further. Like, again, I randomly wrote down a string, so I don't actually know what this simplifies to, but often you can simplify it, and that would be an application of Boolean algebra theory. But why do you want to simplify it? Well, so that you have a shorter expression, so that when you're actually manufacturing some kind of component, you don't have to use as many of these digital gates on your circuit board. So that's why one reason why you might want to study Boolean algebra is so that you know these rules for simplification, so you can simplify things. Here you're simplifying by hand. In the textbook, you'll see a discussion of a method for methodically simplifying these to make expressions as short as possible. I also want to mention that in your homework you studied NAND. So P NAND Q, which for today and also in your textbook it's written as P up arrow Q, but I'll continue to pronounce it as P NAND Q. This is not P and Q. And you produce truth table for this in your homework. Now, what good is this, for example? This is very useful in digital electronics for the following reason. Suppose I wanted to calculate not P. Well, by idempotence, you know that you can also write it as not P and P, and then that turns into P NAND P. So instead of using a NOT gate, you can use a NAND gate to produce the negation behavior. Similarly, if you wanted P and Q, let's see. So I think I can negate it twice. So double negation, you know that is the same as before. And I think in terms of equals, we've been writing double arrows, so I better do that. Okay. Here I'm defining notation. Let me use double arrows everywhere. Okay, so double negation. Let me group this as that, and you see this is negation of the negation of P and Q. Well, that's simply this thing. That's P NAND Q. But negation of something, we just figured out above. We just take that something and repeat it twice and NAND it together. So I don't know why I keep writing equal sign. So equals, and to negate something, we simply take that something, write it twice, and then NAND it together. So if you want P and Q, you can calculate it using 3 NAND gates instead. Finally, if you want P or Q, you know that by De Morgan's law, it's not P and not Q. And so that's equal to the NAND of not P and not Q, right? Not and, so that's the NAND. And then this, by what we figured out above, not P is P NAND P, and not Q is Q NAND Q. So again, we were able to rewrite OR using 3 NANDs. So in this way, what have we just shown? Mathematically, we've shown that every Boolean behavior that we would like can be encoded using AND, OR, and NOT. And then we further showed that AND, OR, and NOT can be encoded by using NAND only. Now, what this means is that when you're creating circuits, you can just use NAND only. And there are these IC chips with a bunch of NAND gates on it. And by using only one kind of gate, you might simplify your circuit. Of course, here you see one operator becomes 3 operators, so there's a cost to by simplifying the number of different kinds of components, like not having 3 different kinds of gates, but only have NAND gates. You are also making your formula longer. But by only using one gate, maybe you can reduce production costs when you're actually making those circuits. So it's important to know and perhaps use the fact that NAND can encode all Boolean functions. Similarly, by duality, you know that NOR can also encode all. Um, so not or. No, you also did that in your homework. NOR is also functionally complete and can represent all Boolean functions. It turns out that in terms of NAND versus NOR, there's like fabrication engineering reasons why NAND is preferable over NOR. I think I remember learning that NAND is faster than NOR, and it also takes up less like physical space than a NOR gate in terms of actually manufacturing these chips. But I think that's beyond the scope of the mathematics I want to show you. So the takeaway is that these things that you're learning, De Morgan's law and other simplification techniques, and also the general setup of Boolean functions, all of this goes into designing of circuits, and that goes into making computers and other embedded systems and other things. Now, this theory is very useful in practice. I want to see how far-reaching some of these mathematical ideas could be. Alright, if you want to know more, take a look at section 12.4 and 12.5 in your textbook. Alright, that's it. Bye.